Hey you guys, welcome back to the channel PHYSICSSIRJEE, and here we are in the JEE Mains Debated Questions series, and this is one of the best possible ways of going through your last leg of the JEE Mains preparation, going through some of the debated questions from the past year's JEE Mains papers. Okay, so here I bring forward the JEE Mains 2013 offline problem in which a condition for the envelope detection of amplitude wave concept was asked. The debate about this particular question was that the final condition that is required to solve the problem, which you could see at the left bottom of the thumbnail, was not mentioned anywhere in the NCRT anymore, right? So how do you approach this particular problem? We would try to see. I would request you to watch this one till the end of the video, because the kind of concept that is involved is a very interesting one and could be a potentially a JE advanced problem when comprehension is mentioned and information is given. Okay, so here we go ahead with the formal wording of the question. In case you have not tried this question before, I would request you to pause the video and maybe try it for 2 or 3 minutes and then do come back for the complete explanation of the concepts all through the problem. Okay, so a diode detector is used to detect an amplitude modulated wave of 60% modulation by using a condenser of capacity 250 picofarad in parallel with a load resistance of 100 kilo ohm. Find the maximum modulated frequency which could be detected by it. So 4 options mentioned, and you're supposed to mark the best possible one. Okay, so let's move forward with the certain concepts that you need to be well versed in order to attack this problem. So the concept number 1 is the idea of envelope detection of a simple sine wave. Okay, so we'll move on to the amplitude modulated wave, that is AM wave, but we should understand how you can detect envelopes of any particular wave. So I picked up a page from NCRT, even though it is not from communication systems, it's from the topic of semiconductors, wherein he discusses the envelope detector for the first time. So imagine there is a AC wave signal, which is a simple sinusoidal wave. As you could see, this is the input that he's talking about, which is input here. A rectifier actually clips the negative part of it. Okay, so this negative component will be clipped off from this side. So if it is a full wave rectifier, this will be made into a positive part. And if it's half wave, only positive cycles will survive. So whatever it is, you could say that this one does a job of ensuring that the positive terminal voltage only will be developed across this X and Y. Now that is fed onto a capacitor, then this output is seen. Okay, so how do you realize this? So whenever the value of the potential difference across X and Y, you can assume this Y is 0, is actually rising, this positive one, then the capacitor actually starts getting charged with a plus sign on the top and minus sign on the bottom. Once it reaches this peak value, the capacitor is actually going to get fully charged. Now the problem is that this particular rectifier, also known as diode detector, will contain a diode here. So once this one reaches the highest possible positive value and this one reaches the peak, next dt seconds later, this value comes down. That means this value would be slightly less than V naught. So with a diode here, the value of the potential here would be at the peak, and here it is slightly less than peak, makes the diode at this place a reverse bias diode. So it would be completely cut off from the input signal. Then this RC circuit will be on its own, right, and it will start discharging. So instead of following the input by going down, this output here would actually stay at this value and start decaying because of this RC decay. Now this decay has not been shown here, but actually it will start decaying in an exponential manner, because in this particular NCRT diagram, they're assuming the value of RC, which is the time constant of decay, is very large. So in general, when the decay starts, remember the input signal is also going to go through this entire cycle, and again it is going to rise from here and it meets this decaying curve at this place. And once the meeting point takes place, the diode here will become forward biased again, and therefore at this particular place the curve will follow the rule. So whenever it reaches the peak, the decay starts and again meets the input signal at its decaying position. So this is kind of a decay thing which has not been shown here. I'll show it in a better diagram in the next slide. So this kind of thing will cause the envelope to be detected. So what is the envelope here? Envelope is the value of the amplitude, which in this simple scenario is a constant envelope. You could see it's almost a straight line, and therefore the output is a straight line. So this is the basis of an envelope detector, where you will have a diode or a rectifier and an RC circuit. Okay, so and the condition for that RC should be such that the value of RC should not be very small. For example, if RC is very small, when this input is trying to rise, this output side may discharge this entire charge immediately. If RC is small, that means time constant is small. Instead of waiting for this one to rise, it will decay immediately at this place. So usually you need this value of RC to be larger than the time period of the input signal. Whatever is the time period of this value should be larger than that. Okay, so this is a concept number one. Now, what is the amplitude modulated wave? Whenever any message signal, which is a simple sine wave, which is a lower frequency signal, is modulated, or you should say it is modulating the carrier signal, you end up getting a amplitude modulated wave, wherein the message signal will behave like the envelope of this carrier signal. Carrier signals are usually higher frequency signals. The science of this particular thing and the theory you should be well versed with from your NCERT textbook. How to build that amplitude modulated wave mathematically, I'll explain in the next slide, but the physical diagram on the graph will look like this. It's almost as if this one is the envelope, right? And this curve is made to sit inside that. That's why this outside curve is called the envelope. Okay, so this is called the AM wave. Now, when a receiver receives this AM wave, its duty is to detect this envelope so that it can gain back the message signal. You cannot throw the message signal directly into the air because of losses that would be occurring. So you make it friends with this carrier signal, make it into AM wave and send it into the air. Receiver receives this AM wave, but what it needs to decode? It needs to decode the message signal. So that's why envelope detection is very important part of demodulating an amplitude modulated wave. Okay, right? So now the concept two that we are talking about is the envelope detection of AM wave. Last time we did for sine wave, now we are going to do it for AM wave. This is again a basic diagram that's given from the chapter 15 of your NCERT textbook, wherein AM wave has already been sent into the air and it is on the receiver side here. You could see this is the detector for the AM signal. Okay. Now, once it goes through the rectifier, it clips off the negative part. As I explained, there will be a diode inside this. Okay, and once this is sent into envelope detector, remember this envelope detector will have the RC circuit as I explained in the previous slide. Okay, so then from this it should be able to detect this envelope so that you get the message signal back. Okay, so I know some of you might be thinking this message signal is not going from sine wave, it is slightly lifted version of the sine wave. A lifted version of sine wave will have a DC component which can be eliminated by placing an appropriate capacitor. That is for another video. Basic understanding of this is to take care of the envelope, how to get through this envelope. Remember, this would not be a straight smooth curve because there will be in between these two gaps the decay of this RC circuit will take place, and that is our focus in our next slide. So trying to enlarge that, we should understand that whenever it is going from peak to peak of this thing, so whenever it reaches the peak, remember the diode in that rectifier is going to not function, that is it is non-conducting, then or it is in reverse bias, then the decay will happen. So this line, you could see the small step lines are the decaying of RC circuit. Okay, and once the decay hits the original signal, then again it will follow the input signal and it reaches the peak, again it starts decaying, it hits the next one and again it follows. As you could see, that is what is going to happen if the RC is not too small. If RC is too small, then just follow my lead here. From this position, if RC is too small, instead of hitting the peak like this, if I go back, you could say if it decays too quickly, then it will fall to zero immediately. Instead of following the envelope, it will be not giving you the desired result. You want it to follow this envelope because this is your message. There is another problem. If RC in your grid, you're making it too large, okay, right? Too small is it's going to discharge immediately. But if it's too large, you could see from this top, it will follow a very small slope, If RC is too lazy, that means time constant is too large, means time taken for decaying is very, very lazy, very, very large. Then instead of following this envelope, this small slope thing will go and hit it somewhere else. So your final detector will think the message is like this instead of it being following this one. So there is two limits that is required for RC. One is the limit that it should not be too small, and another limit tells us that it should not be too large. Okay, so our job here in this problem of JEE mains is to determine the too large quantity part. Okay, it should not be too large, so it should follow on this particular line. Okay, I hope you get this point. So just to sum up whatever I said in this particular video up till now, these are the things, right? So when RC is too large, it will miss the envelope. When the RC is too small, it will actually decay very quickly. What you require is the correct RC, which is somewhere in between them, so that the value of RC on vague idea in NCERT that he has given is that it should be larger than the time period of the carrier. That means this is the time periods of carrier. So it should be larger than that so that it doesn't decay very quickly. But it should be also smaller than the time period of the message signal. Message signal is the envelope one. So let's say the time period of the message signal I have marked in red here so that you can easily see this, and it should be smaller than the time period of that message signal. So the vague idea, if you read the text below the diagram that I have shown in NCERT, this one, you try to search for figure 15.13 and read the paragraph under this, they will give you a vague idea that RC should have limits of this. But this is not the completeness. Okay, so because the right side limit, you can get it even a better value if you want to avoid the negative clipping. This idea, when RC is too large and you are avoiding this envelope while fall is happening. Remember, all the danger is when the signal is falling. Okay, so when this fall is happening and you want to avoid the negative peak clipping, then you need a better value of RC than this particular estimate, which is a vague idea given in NCERT. That is where our problem comes into picture. Okay, so just give me the result first and then we'll try to prove it. So for better detection of the modulated signal with the diode detector below, one requirement is that the time constant of RC filter conforms to this one. So 1 by omega C is fine, but that 1 by omega M thing that I wrote in the previous slide, it should have a better condition. Now modulation index is also coming into picture. So this particular part of the expression was the crux of your JEE question, how to prove this. Okay, so that is what we are going to deal with in the actual solution. Okay, so with this basis and foundation, let's move on with the confidence to get to that expression. Okay, so a lot of things on the board. Just follow my lead. It is going to be fun ride for people who understand this. Okay, so look at this one. So I've enlarged that part where your discharging takes place. Remember, once the peak is hit, the RC circuit is going to discharge. Actually, this line is supposed to be a exponential curve like this. Okay, but we can make some assumptions here by assuming there's a straight line. Why can we do that? I'll explain that. Okay, so the actual envelope is this one, which is your message. You're supposed to follow this curve, but there will be an error. You'll be getting this kind of a curve. Okay, if RC is too large, then you'll miss the envelope by having a slope like this. So that's the danger. So step by step, let's write the AM wave. Whenever AM wave in voltage form is written, it is written in this form where E naught sine omega ct is the carrier wave, and you should know by now that the amplitude modulation is where you will take the message signal, omega mt is the message signal, and push it into the amplitude of the carrier wave. That's why it's called amplitude modulation. When you do frequency modulation, you fit it in the frequency. Here you are fitting the message signal inside the amplitude of the carrier wave. That's why it's called AM wave. Now, what is the envelope of any product of two functions? You should know that the envelope of any product is given by the lower frequency function. So for this bigger frequency function, this blue colored thing, lower frequency one, is called the envelope. Okay, so which is E naught into 1 plus mu cos omega mt. Because of this 1 plus only, you'll get that lift. As I said, it's not the straightforward message, but a lifted message signal, 1 plus something. Now the discharging capacitor voltage, we all know that it should be E into e power minus t by RC. What is this E? E is the EMF or the voltage at any arbitrary position. It could be E here, it could be E here, because it hits the multiple peaks, right? Which is also a function of time. One of the peaks, right, let's say is E naught. From here, if it is actually going down, it would be taken as E naught. Any arbitrary position, it should be considered as E. Okay. E itself is a function of time, which is this one. So that itself is going to decay as a function of time whenever the discharging takes place. Now, since RC is already as admitted to be larger than 1 by omega c, remember we are here to find the upper limit, but lower limit it is far away. That means RC is large enough to be considered to be a straight line. Okay, right? So in that scenario, e power x, I can write the Taylor series for this, right? 1 plus x square by 2 factorial, so on and so forth. And with RC being large enough, you can consider this T by RC to be small, so that you can write that as 1 plus x term. So first two terms of the Taylor series I have taken here. And that is why you are able to realize that this is a linear term under this approximation. If it's falling very steeply, then you can't do that. As I earlier said, it should have some limit. Okay, now with this function, it is here, you are going to now get the upper limit. Upper limit is given by the logic that, follow this carefully. Imagine if the slope of this particular line is somewhere like this. Okay, instead of this black line, if it were red line, you will miss the envelope. So I'll make a statement that the slope of this E naught into 1 minus T by RC term should be greater than the slope of the envelope, modulus of it. Obviously these are negative slopes, right? So because if it is too small a slope like this, then it will miss the envelope. So out of the two, the envelope and this function, whose slope should be larger? The slope of the capacitor discharger function. Okay, so slope is given by dv cap by dt. Modulus, because it's a negative slope, should be greater than or equal to the d by dt of the envelope. The envelope is this one. That is the condition. Okay, right? So with that condition in our hands, we'll try to substitute the required conditions here. So differentiation of this gives you E by RC, and differentiation of this gives you this. And let's go here, follow my lead, right? E by RC. So E is substituted from this function, envelope function here, and you end up getting this blue inequality. And take RC on that side, bring these things down, then you'll end up getting RC is less than or equal to 1 plus this cos function divided by the sine function. It's not yet done, so I need to find the maximum value of this function, so that I can write this one less than or equal to some expression wherein we expect the final term to be what I started out in the previous slide. Okay, so for this part, if I copy it to the next page here, okay, call this as f of t, right? This f dash t is equal to 0 gives me the maximum of this. Okay, so for that, the condition is to differentiate this function. Instead of taking the coefficient rule, I wrote this as mu omega m. I'll remove it because anyway I'm going to equate it to 0. There's a 1 by sine, right? It's a cosecant. Cosecant's differentiation is this, and there is a cos by sine, which is cot. Cot's differentiation is this. I'll get a condition that this once maxima occurs at cos omega mt equal to minus mu. I checked the double differential also. I didn't write it for the length of the video. So substitute this one back into this to write RC is less than or equal to this particular number. When cos is minus mu, sine would be square root of 1 minus mu square. Okay, so that's what ended up with the cancellation of the factor, this one. And this is how we prove that final expression. So from the given numericals in the question, R was, I think, some number of ohms, C was 250 picofarad. You should be able to take this omega on this side, right? I wrote it in frequency, so 2 pi stays here, RC comes down. Mu was given as 0.6, I think 60% modulation, so 0.6. When you substitute, you get the value of 5.31 kilohertz. So if you go back and try to search for the options that are given, I think you will find one of them, which is 5.31. In the internet, a lot of wrong solutions are given, but this is the exact one, which is unfair on JEE mains part, that it's not discussed in the NCERT at this particular level, and they have asked it, and they have never repeated this again, but there is a good chance that it can repeat because it's a previous JEE mains question. Okay, so I hope you enjoyed this particular discussion on this. So there are many more JEE Mains debated questions in the series. A link of that playlist is in the description below, and also the parallel series that you can see on the board right now. If you're new to this channel, please do check them out. All the links are in the description below, or directly go to the channel's playlist and you can see all the playlists. Topic wise I also have arranged so that people can go through them easily. Okay, so if you have no idea about any playlists and everything, I would suggest you directly go to the videos and start watching them from the first upload to the last upload. 3 videos per day, I think you will be ready with your preparation over a period of time. And you'll also understand the quality of the problems, and the concepts that are taught on this channel are unique, and they require a like, I guess, and the channel requires a subscription. Okay, so I hope you have done that, and with that confidence I sign off and see you in the next video.